Hello. Thank you everyone for joining us. I know it's the graveyard shift and we're standing between you and your plans for the evening in this beautiful city. My name's Stephen Gordon. I'm a product manager at Red Hat focused on KubeVirt. I formerly worked as product manager for OpenStack Compute and on Red Hat Virtualization. I'm joined by Stu Gott, who's one of our engineers working on KubeVirt. Today we're going to walk you through the project a little bit. So I'm going to give a high-level overview of what KubeVirt is and some of the thinking that went into why we built it in the first place. Stu is then going to go in a deeper technical dive and also do a demonstration of some of the things that it can do today. And then finally, in closing, we'll talk about some of the things we want to do in future. So first of all, just to contextualize the presentation, I want to talk a little bit about the story so far for virtualization in a containerized world. So that first of all, the most common intersection of these two technology categories, for want of a better term, is I need a place to install, run, and manage Kubernetes clusters, or container clusters for that matter. So depending on which analysts you believe, 60 to 80% of container workloads today run in virtual machines, be those on OpenStack, on OVIRT, on VMware, or on the reigning public clouds. What we're envisaging is that while that's true today, there is still a percentage of people running workloads on bare metal, and that is going to increase in future and be more appealing to people for the application containers. The second most common intersection of these technologies, and the one you've probably heard the most about this week here at this conference, is I need a way to provide strict isolation of application containers, typically leveraging hardware-based virtualization technology in projects like Kata containers and gvisor, and that's something that obviously has been a hot topic. So those technologies are focused on I have an application container and I want to use virtualization as a way to provide strict security around that application container. But the question we asked ourselves is, what about existing workloads? So a number of years ago now, I think 4 years ago, Red Hat made a big bet in jumping in with Google and others on Kubernetes as the future of orchestrating workloads across the data center and the public cloud for that matter, or as we refer to it, the four footprints of the open hybrid cloud. But we know that there's a huge fleet of existing virtualized workloads out there that have been built up over the last 1 to 2 decades, that the technology's really been commonplace. And that those virtualized workloads aren't necessarily going anywhere fast. That can be for business reasons, in terms of it being tough to build a business case to containerize every single virtual machine you have in your fleet. It can also be that takes time and that causes you time to market issues. On the flip side, there are also technical reasons you may not be able to containerize a workload immediately. So if it's using a different operating system to the one you want to use on your container hosts, using a different or older version of the kernel that you want to run on your container hosts, or if you're using things like custom K-mods that, again, you don't want to expose as part of the attack surface of the Kubernetes nodes themselves. So in essence, we're thinking about how can we bring these two things closer together, our orchestration of container workloads, but also virtual machine workloads. How can we make those managed and interacted with in a more common way than they are today, where you're effectively using two separate management layers? So if we think about virtual machines and containers, we have a virtual machine effectively virtualizes hardware, and a container isolates processes. And each of these gives the workload, or the footprint for the workload, positive or negative attributes in terms of a trade-off between performance, density, and security. But increasingly, most organizations at this point have a mix of both, those existing virtual machine workloads, but also new applications they're writing in containers. So we have these existing systems that treat these separately, and we kind of have this transition we see as going, where we started off with virtual machines running on a physical machine. People started adding containers to those because a virtual machine was effectively the easiest way to get compute resources in their organization. But as containers become more and more commonplace, we think we're going to see this flip where more and more of the containers are going to run on bare metal, but there's a desire to keep virtual machines running alongside them. And when we think about the Linux virtualization stack as we work up from the hardware, we have a Linux operating system, so effectively the Linux kernel. we have the KVM kernel module. But then on the user space side of the equation, we have QEMU processors. And although they need access to the dev KVM device, they are at the end of the day just processors. And if there's anything we've learned in the last couple of years, the rise of containerization technology in Linux, we can take a process and we can put that in a container. And by doing so, the thinking is that we can take advantage of many of the things that Kubernetes can do for us in terms of placement, network security, isolation, quotas, etc., and share those capabilities between both the application container workloads and the virtual machine workloads that we want to run. So effectively taking these two separate management planes and combining them using Kubernetes as that common element. So what is KubeVirt? KubeVirt is a technology enabling Kubernetes as a unified platform for building, modifying, and deploying applications, regardless of whether they reside in containers or virtual machines in a common environment. So effectively adding virtual machines to your Kubernetes project or namespace as easy as it is to add a new application container. We do that via implementing a custom resource definition, or actually increasingly a number of custom resource definitions. What that means, some people may have heard this concept referred to as third-party resources in the past, but it's a way of extending Kubernetes to add new top-level API objects, in this case a virtual machine. And it's a pattern that you're going to see more and more of in coming years as the Kubernetes community tries to keep the core of Kubernetes itself relatively small, while allowing plenty of extensibility for new ideas like this to be built around it. So in that manner, we extend Kubernetes so VMs can be scheduled alongside containers by effectively making the virtual machine look like a pod to the Kubernetes scheduler, so that it can be scheduled in the same way as any other pod that just contains a normal application. Wherever there's been a decision point around how to implement something from a conceptual point of view, we are attempting to take this opportunity to reimagine a little bit the way we think about virtualization and to take as Kubernetes a native approach as possible, so that interacting with these virtual machines in the system is as natural as possible and feels as much of a common workflow as it is to interact with the application containers. So in terms of working through a basic use case for this, we'll start with a legacy VM that we have in our environment, and let's imagine that that VM is hosting an API or a service that our business relies on. And we know right now we don't have a business case to containerize that immediately, but we want to continue to expand our capabilities and build services around our existing capabilities. So we have the opportunity to bring that virtual machine using KubeVirt into the Kubernetes environment. And then we can start building our microservice applications around that, testing them against that legacy virtual machines APIs. And then if we choose to at a later date, we still have the ability to take some of that virtual machine and start decomposing it into application containers. And the beauty of this is that we can now schedule our complex application all as one unit, be it using OpenShift templates, as we will in some of our examples, but also using things like Helm charts and other Kubernetes native constructs. Via this mechanism, the idea is that we can finally bring these two types of workload together, and the resultant virtual machines can run side by side on the same host. So there's also some potential consolidation gains there in terms of our ability to pack a host with both virtual machine and container workloads side by side. We do also have the ability, through using Kubernetes in this way, to leverage multiple existing ecosystems. So at the moment, the virtual machine networking, we plug directly into the same networking as other pods. We also have the ability to use storage both from the Kubernetes ecosystem, but also from the OpenStack ecosystem via the Cinder plugin for Kubernetes. One of the interesting things there, and where we're continuing to work with a number of the storage vendors, is around defining the container storage interface spec for Kubernetes, because we have a strong interest to support virtual machine workloads which require some storage capabilities that normal Kubernetes workloads don't necessarily currently have to care about. So things like cloning are very important to us, and there's no standardized way to expose that in Kubernetes yet. But that's something where we believe that bringing these types of workloads to Kubernetes is also going to allow us to improve the base that we're building on for everyone to take advantage of as well. So at this point, I'll hand over to Stu, and he's going to take you through a bit of a deep dive of the technology.
Thank you. So I'm probably going to cover a little bit of the same ground that Steve did, but that's actually okay because repetition builds retention. And historically, this has been a kind of a deep talk. As Steve mentioned, we use custom resource definitions to actually model the virtual machine objects that we use. I've got an example of one up here on the right. The advantages of doing that is that it is, absolutely as Kubernetes native as possible that way, because anybody that's familiar with Kubernetes, and actually show of hands, who is familiar with Kubernetes at this point? Okay, fair enough, about half and half. So yeah, as far as these definitions go, it's all YAML, which is very human readable in terms of configuration. And inside of our custom resource definitions that we're setting up, we're aiming to be as expressive as possible in terms of what virtual machines are going to need. So whether that's networking stack, the NIC card that you're using, the model of the architecture, the number of CPUs, memory, all that sort of thing is in that manifest. In our example here, we have 1 gig memory. The feature set that we're targeting is as close to libvirt as possible, and that's a very good reason for that. We're actually using libvirt under the hood on each of the pods. And as far as implementing it as a CRD, we also benefit by gaining any sort of Kubernetes isms for all of the resources that Kubernetes manages. Now, as far as the CRD goes, we would, if we just defined that and left it, it would just sit there. If you uploaded a virtual machine object to the Kubernetes API server, it's not going to do anything. You're just going to have a record on the system. So this slide sort of models out how we actually put that together, and it's kind of information dense. So I'm going to spend a minute here. As far as the KubeVirt model, we use the operator pattern from Kubernetes. So the virt controller and the virt handler are working in tandem to kind of handle each of the different resources as they're being pushed around. Now, I've used a custom resource here instead of virtual machine, being deliberately evasive about the actual name of that, and we'll get back to that. But the virt controller actually monitors for these virtual machine objects using a lister watcher or a shared indexer, which is a Kubernetes object. The reason doing that is so that it's actually scalable. You don't want to make synchronous API calls, for those familiar with Kubernetes or unfamiliar, because it overloads the system, and this needs to be scalable. So we have one centralized controller on a master node, which is actually handling all of the virtual machine records. And its only job is to take those virtual machine records and actually schedule a pod, which I've got on the right-hand side. And so the virt handler will see the existence of that pod and know that it belongs to the virt handler because of a label on that resource, and schedule with the libvirt daemon running on that pod to actually start the virtual machine, which is at that point a libvirt domain. So as far as the virt controller, there's one per cluster. You only need one, and it's on the centralized system. As far as virt handler, you have one per node, and it's monitoring only for objects on that node. And that dichotomy allows things to be distributed and to scale a little better. As far as scheduling, we just talked about that. Virtual machines are scheduled as pods, and in fact, we could actually say virtual machines are literally scheduled via pods. We schedule a pod and then put a virtual machine into it. By doing this, we get the same set of features that you would for any pod, such as affinity or anti-affinity, so that you could say, hey, the pod, the node named foo, this machine is incompatible with that. Or using labels and selectors, much the same. Or you could even write a custom scheduler if you needed, because anything that is fair game for pods is fair game here because we're using pods. And because we're using pods, each of the network services that you might need to expose on the virtual machine, such as if you've got a MySQL server, you could actually use the exact same services and routes that Kubernetes uses for pods to do that. Once again, you can use labels and selectors to determine that. Now, because virtual machines live in pods, they're transparent to the higher level, which is something that Steve sort of touched on. In terms of the management, you're only managing the pod. The fact that the workload on that pod happens to be a virtual machine is irrelevant. And so that's basically what we have today anyway. Now, when virtual machines leverage the pods by doing that, the metadata, so for instance, the labels, annotations, what have you, and I'll show that a little bit of that later, we can actually take advantage of each of those sub-resources in order to do a little accounting. We get the CPU and memory resources, especially the memory, comes via the pod directly. Affinity and anti-affinity, once again, so you can schedule the node that you're going to be on, as well as the storage, which we'll get into in a bit. Actually, we'll get to it now. So as far as storage, the way that pods work in general is you don't put any data that needs to be permanent on the pod itself, because that's supposed to be ephemeral. You stop the pod, restart it, or delete and re-add, and your data is gone. So the method that Kubernetes gives for pods for persistent storage is called a persistent volume, and is bound with a persistent volume claim. We use those one-to-one inside of KubeVirt, where every persistent volume that is declared in the virtual machine manifest will be mapped into the virtual machine. We give you a way to either use a mount point or a device node in order to put it in the correct spot. Of course, it can be mutable or immutable. For instance, if you had one common boot path of slash as far as mount goes, you wouldn't want that to be necessarily shared or to be scribbled on by one VM if it was shared. So you could set it to be read-only and then allow multiple uses of it at the same time. Or it could be immutable, or mutable, excuse me, where it was actually for your application program data, for instance, a database, where from one boot up to the next, it needs its non-transient memory. And as a side effect of using the Kubernetes persistent volume methods is that anything that Kubernetes can do, we can get as kind of a side effect and just come along for the ride. And so, in terms of the different goodies, such as Cinder, Ceph, Gluster FS, any of them, we're agnostic to that because Kubernetes supports them. But the thing about persistent volumes is, for a newcomer or beginner, there's a little bit of friction because they're not exactly easy, I guess, to set up. So we are developing a couple different utilities that are alongside KubeVirt that can actually help in that arena. So the containerized data importer is one of them, and that's actually on GitHub. That is a link, if you get a hold of this slide deck, that links to the KubeVirt/containerized data importer. This is a declarative Kubernetes utility. It works much like the operator pattern that KubeVirt itself uses, where it monitors for virtual machines that have the specific markings that are needed for this. The two use cases that we've identified at this point are either to download an image, for instance, just a URL, so that you can obtain an image and just insert it directly into a virtual machine and go. Or we have the notion of copying an images from a read-only Kubernetes namespace. And what that basically means is you would designate, and it's up to you as the administrator of your cluster, a namespace that each of these containerized data importers from other namespaces would be able to use in terms of copying the data out. So you could just have a list of persistent volumes that could be copied, cloned, if you will, to a different namespace and then used. That way, if you had one golden master sort of repository, you wouldn't want that to be messed with, but it would be able to be duplicated as on demand. One of the other projects that we're using in terms of trying to make this a little easier is Virt v2v. Once again, it's under the KubeVirt GitHub repo. The approach here is, instead of taking a disk image from somewhere, it's taking the entire virtual machine from other sorts of solutions, such as VMware or an OVA. There are some limitations, of course. It needs to have just a single NIC, and the reason for that is because we only have one NIC that we can define on the KubeVirt side right now. and it can only have one single attached disk. And the reason for that is that we don't necessarily know the correct order of the mount points if you've got them nested on each other. So a little bit back to networking. I talked a bit ago about the services and using routes, but to just kind of dive on that a little deeper, we're using the regular pod network with virtual machines. And basically what we're doing is we're taking the IP that is assigned to the pod and we're proxying it over to the virtual machine so that they appear to be the same entity. A couple good reasons to do that. When migration is in play, which currently it's not working, and I'll get to that in a bit. When you're migrating, you want to keep as much of your identity as possible across that process. So you want to keep that IP the same if possible. There's also no difference in terms of accessing via the pod or via the virtual machine. So label selectors, I'm going to move a little faster here because I'm noticing the time. Kubernetes is doing some work in this area as well. They're actually trying to expand the different networking features that they have, and we'll be able to take advantage of that when that's mature. Offline and running virtual machines. So far we've been talking about virtual machines as a native Kubernetes concept, and that is kind of with the declarative notion that if it's defined, it's running and it exists. But of course, those coming from a virtualization world understand that's not great in terms of how we actually like to work with and model virtual machines, because we don't like to delete them and then reassign literally the entire resource stack from nothing in order to start it again. And so we introduced this concept of an offline virtual machine, and one thing to note about that is there's discussion right now about renaming it, so that the one thing that we can agree on as a community is that the word offline virtual machine is very confusing because it's not offline. It basically represents something that's stateful. It could be online or offline. And so it's causing a little bit of cognitive dissonance. So we're trying to get away from that nomenclature. But for the purposes of this demo, because it's still physically named offline virtual machine in the GitHub repo that I'm going to be demoing, I have to call it that right now. But basically it allows you to define a virtual machine without actually starting it and running it. And we actually use a running equal true or false flag inside the record itself to determine what state the virtual machine should be in. And that compares, of course, to the virtual machine that we've already talked about throughout this presentation, where we define the virtual machine, start it up, it starts the pod, etc. And that virtual machine is actually inside the template section from the offline virtual machine. And so this is sort of how pods do it with deployments right now. We also have a VIRT client tool, which is separate from kubecontrol, which is what you can use most of the time. There are unfortunately a few different features that don't exist in kubecontrol, and there's no real easy way to map them. For instance, the console or VNC, if you wanted to connect that way, because it takes a continuously running socket, that does not work well inside of a REST server. So we need to create a client that's able to look that up and proxy that for you. We also have starting and stopping of offline virtual machines, which will probably be named to virtual machines at some point soon. And the reason that that's here, I'll actually show that in the demo, but to do it with kubecontrol itself means modifying a record on the fly, and that's it's a little unfriendly to do. So this VIRT control can actually either be a kubecontrol plugin, and the syntax is below, or it can just be literally the word virt instead of kube and kubecontrol. All right, well, time for a demo. So I will give you a little bit of familiarization about what this environment looks like. It's running a single node, which I've named node 1 in this case. And I'll just show you what the system namespace actually looks like. The 4 lines here on the bottom, these are actually KubeVirt specific. Everything else is actually Kubernetes. So we've got Virt API, which is it's a proxy that basically takes all the KubeVirt native calls that we handle, and if it doesn't recognize it, sends it on to Kubernetes itself. That's a little contrary to how Kubernetes wants to do it, but we got there first. We implemented this before they had the concept of a user API server, which we would love to move to, but there's been a little difficulty with you have to ship your own etcd server, and that's a little difficult. Virt controller, as I mentioned, we have 1 on the system. You see 2. The reason why is there's actually 1 that's for redundancy, so it's actually lost the leader election and is not active right now. And because I only have 1 node, I have 1 Virt handler. And so this is actually just straight off of the GitHub repo here. And so this manifest actually exists if you wanted to clone the repository and look at it. But what we've got here, and this is the virtual machine I'm going to boot in a second, is a Fedora image that's requesting 1 gigabyte of memory. We're injecting a password of Fedora for that user account. So if I want to go ahead and show you, there are no pods and no VMs currently running. But when I create this, and look again at pods, I've already got one, and you see it says container creating. And if I look at the virtual machines, and I'll actually expand using the YAML flag, you see it says that it's in phase scheduling right here. This line right here. So in a moment here, the pod is now running as I was talking. And so if we look at that YAML again, the virtual machine's actually running. And we can actually connect to its console real quick and show you that that actually is working. And it's just a standard boot sequence that you're familiar with from other machines. I'm going to go through that process. I don't know if we need to necessarily sit there and watch the whole boot sequence, or there you go. So can even log in Fedora, and the password was Fedora from the manifest. You could change it right there if you wanted. And so there you go. That is a virtual machine. And if I want to go ahead and delete that, I use, we're deleting records because we're in the declarative sort of model here. And that will actually clean up both that and the pod will be terminating here and will actually disappear in a second. Would also like to real quick show offline virtual machines, and we have an example in there as well. And we want to look up the Alpine multi PVZ. So this is basically very similar. We're only going to request 64 megabytes of RAM. In this case, we actually have 2 persistent volume claims that we're using. We've named one VIRTIO, or excuse me, PVC disk 1s and 2. Otherwise, one of them is actually the Alpine image, and the other is just blank, actually. So it would be used for data storage if we needed. So if I create that, now in this case, I have an offline virtual machine created. And if you look at the YAML that is created here for this, you see it running equal false. This is basically saying we've defined the virtual machine, but we haven't actually started one. And you can see that if we go in and look at the virtual machines, there's just not there. So as far as this VM or OVM, if I edit it, come in here, and instead of false, we'll change there we go, if I can type. And at this point now, if we look at VMs, it has started one. And so it's kind of the same process as before. Obviously, doing that every time you wanted to start or stop a virtual machine is not ideal. And so as I had mentioned, we have the virt control command that actually has a stop. In fact, if I just run it, it'll show you the commands that it actually has available to it. So stop, OVM, Alpine, multi-PVC was it? That's a mouthful. But if you then look at the virtual machines no longer running, and if you look at the offline virtual machine, it should say stopped again. Because that's all that is, that command is just a shortcut to actually edit this running equal false flag for you. So as far as the demo, I think that's pretty much all I wanted to show there. So I will turn it back over to Steve for future plans.
All right. So first of all, I just want to talk very quickly from, so we focus mostly on the KubeVirt project. From a Red Hat productization perspective, at the moment we're really just focused on getting a preview of this technology into people's hands. And you can see here an example of that from the OpenShift service catalog. So the idea is that this summer, if you're an OpenShift customer, you'll be able to access that tech preview. But of course, if you want to try the community bits, and I'll have the links up on the screen in a second, you can go to the KubeVirt repo. You can grab the demo script from the demo repo under that organization and basically run what Stu had running here today for the most part. All those YAML files are there. Running or installing KubeVirt on a cluster is fairly non-invasive, so it doesn't need to modify the host directly. You basically deploy it by running manifests, so we also have some Ansible playbooks to help you out as well. In terms of future plans from a wish list perspective, some of the things we want are additional VM lifecycle actions. So at the moment, we demonstrated start and stop. We'd like to do things like reset and hibernate in particular, because I think Stu mentioned the current corollary to idling. Hibernate would potentially get us a concept much closer to actually idling the VM than we have today. Supporting more turnkey storage solutions. So we mentioned that via the interfaces we have, we can theoretically use any storage solution in the Kubernetes or OpenStack ecosystems, but we need to test more of those and get more of those into CI. Networking, at the moment we're cheating a little bit. We're taking the IP from the pod and giving it to the VM. We would like to use multi-networks to actually have an IP for the pod and for the VM, but also to enable things like SRV, sidecar containers for Istio, and so on. And then the other thing that we're focused on is thinking about how can we get the VM constructs into things like replica sets, daemon sets, and other Kubernetes-like constructs that people want to use for scheduling their workloads. So in terms of community, at the moment this is in a GitHub organization. We have a mailing list. On the website you will find instructions for running KubeVirt on a number of common platforms, so things like Minikube, Minishift, and so on. And also we're available on IRC and Twitter. At this point, I think we have a little bit of time for some questions, and I see someone's been waiting very patiently at the microphone, so fire away.
Very innovative concept. Essentially, I see it's the inverse of Kata, where you try to do lightweight VM and try use container within them. Here you are taking containers as a process and trying to put a VM into it.
Yes.
So it's an inverse process. My only thinking is, okay, you do have use case you are mentioning, but in production, it's okay as long as you are talking about what do you call the storage aspect of it, because you want to get use cases for trying to save the whole set of things or duplicate them and replicate them and all those. That's fine. But in production, do you think this will have a use?
Yes. So I just want to touch on the Kata versus KubeVirt thing quickly, again, just to start. So one of the things I should have mentioned is we do see Kata as very much a complementary use case, not competitive. So we see a world where both of those coexist to some degree, because both have value to add for those separate use cases. And we actually, also because we're sharing the KVM and QEMU elements of the stack, we have worked quite closely with Intel and others on how we can continue to improve the Virt stack. In terms of seeing this used in production, I think we see it as a somewhat inevitable reality that people are going to have workloads that are composed of both virtual machines and containers that are part of one complex application that they want to orchestrate together. And in terms of an emerging technology, we see this as a very promising approach to doing that. I mentioned from a product standpoint, we're only looking at technology preview this summer. We don't have a fixed roadmap right now for when we'll go to full production support. But certainly the plan is to get there, but we're going through that planning process right now. And part of that is putting it in people's hands and basically taking feedback. We're very interested right now in what people want to do with the tool and taking that into account as we plan kind of beyond this initial preview phase.
Okay, interesting. We'll watch you. We like this.
Thank you.
Thanks.
Hi, this is a question for Stu. There are a few projects in this space. Can you talk a little bit about the design decisions that you took with KubeVirt and compare it with other projects and see what worked, what didn't work, and what worked better in your case?
So our main use case, of course, is to work with Kubernetes in order to make sure that we have a distributed workload that can actually be managed at the cluster level. As far as some of the other solutions out there, we've mentioned Kata containers, of course. I'm sorry? Virtlet. I'm going to have to think.
I can probably take some of that because I think that goes back further into the history of the project. So I think for people who don't know, so I mentioned KubeVirt is defined as a custom resource definition, which means it's a top-level API object. Virtlet integrates at the same layer as Kata containers, so it's a container runtime interface implementation. So what that means is that when it comes to all of the features of the virtual machine, or the knobs, as you will, they put it through the metadata annotations because they don't have a top-level API object. For Kata containers, that works quite well because the metadata annotation typically is just, am I trusted or not? For a full virtual machine workload, we felt that was a little problematic because once you really get into all the knobs that traditional workload expects, then your metadata blob becomes quite expansive. And we really wanted to, like when we look at the complexity of the existing libvirt XML, for example, we wanted to have a rich API object to interact with. And also, we have to have objects for other things as well. So for example, right now, we have a concept of a virtual machine preset object at the top level. We didn't show it in this demo, but it's very similar to a flavor in Nova, for example. We also expect at some point we'll have a migration object for things like live migration. So the approach we take with the custom resource definitions allows us to provide a much richer interface to the VMs. And also, one of the underlying things is we know we want to take a traditional workload and ideally make it so you don't have to change it at all to be able to bring it in, although you may change it later, as I mentioned, to start decomposing it. And those things typically expect a lot of very specific settings depending on the workload, and we know we're going to need those. So the objects give us a way to expose that in a very neat way to the user. Hopefully that helps a little bit. I mean, obviously I'm a product guy, but that's my recollection of some of the primary reasoning.
Hey, sorry if you already answered the question in the talk, but do you share the same registry as the Kubernetes one?
Yes.
Okay.
So in most of our demo scripts for simplicity, like the Alpine image and the Fedora image are coming straight from Docker Hub, for example. We can also use Quay, obviously, and other registries. Where we mention the cloning around storage is in a realistic production deployment. What would actually happen is we have a concept of a template, And for fast instantiation, you want to be able to use storage-assisted cloning to bring that template into a new VM each time really quickly.
So at the moment, each time you boot a VM, you're always fetching the image?
If you set it up that way, you don't have to. So even now, we can use the storage-assisted cloning if it's there. But in the really simple demo example, we just pull it from the registry because we don't want to have the overhead necessarily. Like if I run it up in Minishift or Minikube, I don't necessarily have a storage implementation there that has cloning. So for those examples, we typically just use the registry. I think Stu's grabbing the actual, yeah.
So this is where our images actually came from. We kept, for demo purposes, we have a container running on the exact same cluster that is exposing these iSCSI images, which is what we were, excuse me, using in the manifests. So, you know, this is what we did for demo.
Okay.
Right.
And are you planning on using a different registry for storing images? So you could have something like Ceph and having copy and write cloning for booting images, and you could also like enable live migration with that. Yeah,
so right now we've primarily tested with Gluster in the context of CNS. We've tested with the registry disks, and we've also actually used Ceph via Cinder as the primary way we vet the Cinder driver, although eventually we'd probably use a native Ceph integration to Kubernetes as well. But yeah, certainly the intent is wherever it's available to take advantage of cloning and storage-assisted migration and things like that. It's just, at the moment, we've really been focused on the very basics, and then it's actually not the storage that's the limitation, it's more of the interfaces in Kube to do some of these things.
No, I'm asking because I haven't seen anything in the roadmap regarding this aspect, so yeah. Thank you.
So for legacy virtual machines that are using CPU pinning or huge pages of multiple sizes, that kind of thing, is that incompatible with this solution?
So it's not incompatible, and having been the Nova product manager at Red Hat in my previous life and lived through this whole evolution of joy, I know that those things are needed, and they are on the backlog as things we want to do. So basically all those things that can be loosely grouped as enhanced platform awareness we want to implement. Some of them are going to be easier in Kube than others because there's a group that's been working on what we refer to as performance sensitive apps in Kube, and they've done some of these things for us already from a Kube point of view, which then from KubeVirt point of view we can just take advantage of. But then there's other things they haven't done yet, and we're going to have to work on the Kubernetes native integration to do that. It's going to
So it has to be available in Kubernetes first.
Exactly. So we get the benefit of all the things that are in Kubernetes, but we get the con of anything we want that isn't in Kubernetes, we need to go and do it, basically. Which, from a Red Hat point of view, we see as a good thing because ultimately we'll improve Kubernetes as well, but it's going to take some time.
Hi. We usually use the customized OS image, which is built by something like Disk Image Builder, which is one of OpenStack project. And actually, I've seen the demo. You just put the container image on the pod spec. And actually, should I another way to build the OS image for this solution?
So on the back end, we are very focused on using raw images, but I think the containerized data importer currently will convert a QCOW2 as well, and we're not getting too far in, like we're not introspecting your guest at all right now, so basically you could use anything that builds a QCOW2 or raw.
Were you asking more of a Rancher VM sort of approach where they actually build the container to be the virtual machine holder?
Actually, pardon me?
Oh, like Rancher VM actually handcrafts the pod and the whole spec around the virtual machine, and it's a one-off. Is that what you're asking? Or
I'm just asking. We can use the legacy image we already built in.
Yes, that's entirely the point, actually, of all of this.
Okay.
All right, I think our time is up, so thank you all for joining us, and you can accost us in the hallway if you want to discuss further, but thank you for your time.
Thank you.